Hi, friends. I'm the Minute Math Lady, but this video is going to be a little bit longer than a minute. This is the full-length explanation of graphing power functions and basic patterns that are controlled by the leading term or the highest power of a polynomial function. In this video, we're also going to briefly touch on multiplicity of zeros and see how that affects the shape of a graph. All of this is to connect the algebra of what we see on the page versus the graph of what we expect to be the visual representation of each of these functions. Because it is important for you to be able to graph a function without your calculator, without the aid of a computer, or at least have an idea, maybe not graph with complete precision, but have an idea of the major features of a graph without using your calculator. We can visually represent and extrapolate a lot of information about a function if we know some basic features of its graph. All right, so power functions, we're talking about x to a single number power. That number power can be even or odd, it can be positive or negative, it can be a fraction or a whole number. So if we're just looking at positive numbers like x to the third, x to the fifth, and these are the numbers that are going to be represented when we talk about polynomials, then the basic categories are odd and even. If I have x raised to a positive odd power, I get something that looks like I'm doing the disco. One branch goes all the way up, the other branch goes all the way down, and all of these functions will go through 0, 0, and you can convince yourself why very, very easily. If I have 0 to the third, I get 0. If I put 0 into my function, I'm going to get 0 out. 0 to any power, any integer, any integer or power that is greater than 0, that's not infinite, I will get 0 as my answer. 0 to the 536th, I still get 0, right? So all of these curves are going to pass through the point 0, 0. You can also probably convince yourself why the odd numbers are going to go through quadrants 1 and 3, and the even powers are going to go through quadrants 1 and 2. Let's just take a very easy example of plugging in the number -2 for our x. If I do negative 2 cubed, I will get -2 times -2, positive 4, times -2 is -8. Negative in, negative out, choop, choop. There's my point, -2, -8. If I put in negatives, I will get negatives out, and that's why I end up in quadrant 3. Over here in even land, if I do -2 squared, I get -2 times -2. That is positive 4, -2, positive 4. And that's why all of my y values need to be above the x-axis. They all have to have positive y values, all my answers, all my points. So these curves in even power is going to only result in curves that exist above the x-axis because they always have to have positive outputs. An important distinction here, just especially in even land, a lot of people say, oh, all of these even shapes are always parabolas. They're not really. Just as a heads up, a parabola is specific to the shape of y equals x squared. A parabola is actually a conic section, has a very, very specific geometric definition of what that shape looks like. Something like x to the fourth or x to the sixth or x to the eighth, they're more rectangular. They're a little flatter on the bottom than a nice round parabola. So anyway, but all of the even positive numbers will have branches that both go straight up. Just briefly, and before we look at leading terms and multiplicity of zeros, if I have a negative power, like x to the -1, x to the -2, you probably remember from algebra class that or x to the -n is really meaning 1 over x to the n. And let's just think about this for a second. If I plug in a number like 10, let's use -2. I get a very, very small output number. The larger the x value I put in, the smaller the y value I'm going to get out, regardless of what this power is. It could be -7, -9. And I'm always going to get a smaller number. Even a negative fraction, like if I had 10 to the -1/2, that's still going to be smaller than 10. It's going to be a fraction with 1 on the top, so it must be a small number. And that is why in all of these graphs, as we approach positive infinity in the x direction, our y values approach 0. As we approach negative infinity in the x direction, our y values approach 0 as well. Our curves get very close to the x-axis. It just depends on whether they're going to get close to that axis from the positive and even land, just like this. I still get a positive answer, right? In even land, if I plug in a negative number, I still get a positive output. Or in negative land, if I did -10 to the -1, I get -1/10. Negative in, negative out, quadrants 1 and 3 for odd powers, quadrants 1 and 2 for even powers. Our last category here of power functions would be having fractional exponents. And again, we have an even-odd distinction. if I have a fractional exponent like 1/3, you remember from algebra class that that really means the cubed root of x. And now as I plug in larger numbers, like the cubed root of 1,000,000 is greater than the cubed root of 2. So if I plug in larger numbers, I will get larger outputs. They just won't grow as fast. Instead of looking like this, where they grow fast, it's going to look like this, where they grow but slowly. There are no horizontal asymptotes in these graphs. They do go to infinity in the y direction. They just take a little bit more time to get there than you would if you didn't have a fractional exponent. Now, what happens here in negative land? I mean, in even land, pardon me. If I plug in a negative number here, if I plug in a negative number up here, the cubed root of -8, I get a negative output, -8, -2, bam. Fine and dandy. This is consistent with what we know about odd numbers as powers producing graphs that live in quadrants 1 and 3. If I have an even number, let's try -4. If I ask for the square root of -4, I freak out a little bit. You might know that that's 4, or that's 2i. The square root of -4 is 2i, and that's great. If I'm dealing with complex numbers or a complex plane, I can think about the number 2i, but I'm not. This is not a complex situation. This a complex meaning including i's and imaginary numbers. This is a real graph. I've got real numbers in the x direction. I've got real numbers in the y direction. There is no spot for 2i on this graph. So when I try and plug in -4, I just can't. And this graph stops at 0, 0 and does not have a branch that goes to the left. All right, so in conclusion, right, if I have x to the n, and that's the only thing I have, I'm going to get a graph that goes through 0, 0 and has one of the finite number of patterns that we discussed here in this little first part of this video. Now, what about having a leading term of x to the n? And by that, I mean, I'm looking at a polynomial that has a lot, polynomial, has a lot of x terms in it, but it starts with something. Maybe it starts with x to the 7 and then has an x to the 6th term, and maybe it's got an x term and a constant. Who knows? It has a lot of things, poly meaning many, has a lot of terms in there, but this leading term means this first one. And it turns out that the highest power of x, the term that has the highest power of x, really gives you a lot of information about what we expect a graph to look like. So for example, let's just take one that you're familiar with. You know that y equals x squared is supposed to look like this. That's our power function. Now, if I add extra stuff to that, let's say I have, I don't know, x squared minus x minus 12, I still get a parabola. It's a little bit off kilter. It doesn't go through 0, 0 like I expected it to. And this one in particular, I didn't draw it super well. It's actually shifted kind of asymmetrically over here. It doesn't even have a nice reflection over the x or the y axis, but it's still a parabola. Its shape is governed by this leading term, and these other things adjust where it exists, and in particular, how many 0 it's going to end up with. Right now, I've got 1, 0, one place that graph touches the x-axis. When I graph a polynomial whose leading term is x squared, now I've got 2. And it turns out that if I graph a polynomial that has a leading term of, say, x to the 5, whatever else comes after it, I could potentially have 5 zeros. I know its overall shape is going to look something like that, because that's what a positive odd power looks like as a power function. But the interior here could actually do some pretty funky stuff. This would be what I'd expect a graph to look like from a polynomial whose leading term is x to the 5th. So some specifics that we can talk about here. We have zeros and we have turning points. The zeros of a graph are the places where the graph touches the x-axis, all of these things, regardless of how that graph starts and ends. If it just touches, if it passes through, this is a graph that has 3 zeros, 1, 2, 3. Okay, a 0, or they're sometimes called roots or x-intercepts. These are the x values where a function will touch the x-axis. And if my leading term is x to the n, I could have up to n zeros. I know that this particular one that I've graphed over here, it's an x to the 4th polynomial. I know that because its shape goes up like this. It's at least x to the fourth. And it has more than 2 zeros, so it's got to be 4. It has an even shape, and it has more than 2 zeros, so x to the fourth, or x to the sixth, or x to the eighth. I could have up to n zeros. I could have up to 4 zeros. I can draw an x to the fourth function that will have 4 zeros, 1, 2, 3, 4, but it doesn't have to. I could actually draw an x to the fourth graph that has no zeros. Yeah. Okay. So that's the zeros part of it. Turning points is the other part of this. A turning point, that's these parts. Let me get a better color there to highlight. These parts of a graph, the kind of tops and bottoms, the places where the graph turns around. 1, 2, 3. 1, 2, 3. All of these x to the fourth graphs that I drew, they have 3 turning points. So if I had a function with a leading term of x to the seventh, I would expect to see no more than 7 zeros and no more than 6 turning points. And because it's odd, I would expect it to do that. Let's look at a couple examples of that, and then we're going to take a quick gander at multiplicity and call it a day. So here are some examples, like degree 2, meaning the highest power, the leading term, I have a power of 2, has 2 zeros and 1 turning point. Degree 3, 3 zeros, 2 turning points. Degree 4, 1, 2, 3, 4 zeros, 3 turning points. I could go on like this forever. You get the idea. Wonderful. Very last thing here is that we want to talk a little bit about multiplicity, because you can see how like the maximum number of zeros, I can change the actual number of zeros on a function very easily just by moving it up and down, by changing the y-intercept, by adding or subtracting a constant. Here I've taken the same basic graph and made it out of 1, 2, 3, 4, or 5 zeros. So I know that this is an x to the fifth or greater graph, and it's going to be odd because it has this kind of end behavior. But I don't know exactly what it looks like. I'm going to focus for just a brief moment here on these zeros. Notice how at these zeros in these two particular graphs, we had a turning point and a zero happening at the same x value. That happens when I have a factor with an even multiplicity. So the multiplicity of a root or a zero is the degree of the factor corresponding to that root. If this is not making sense, you can stop this video now and you'll have an appropriate understanding of power functions. But if you want to learn about multiplicity, hang on for one more minute. And the behavior of a graph near a zero is basically the same behavior of the power that function has at that multiplicity. So for example, here we've got some matching. 1 is C. It has zeros at 0, -2, and +2, and there's nothing funky about them. If I multiplied everything out in C, it would start with x to the third, have some number of x squared, some number of x's, and a constant term. And so I'm looking for an end behavior of this. The only one I have there is 1. Now the rest of these I'm going to match up based on where the squared comes. So I guess I could real briefly point out, like here at y equals 0 or x equals 0, x equals 2, these factors in part C all have a degree of 1, x to the 1, x plus 2 to the 1. That would be a line. And all of these places where this curve intersects the x-axis, they look like lines. If I'm looking at the graph on number 2, I've got something that looks like a line, something that looks like a line. And here at 0, at x equals 0, I have something that looks like a parabola. That matches with D. At the factor that gives me a 0 of 0, where x would equal 0, creating a 0, the term says x squared, not just x. Here's another one. Here in 3, I've got a parabola-looking thing at x equals -2. So I'm expecting this function to have a term that gives me a 0 of -2 with a square on it. That's A. And by default, that means that our last one here, 4, has to be B, and let's just make sure that's true. Yes, at x equals 2, I have something that looks like a parabola x minus 2 squared. Fantastic. We're going to do one example here where we graph this by hand. So for this particular function, I've got zeros at 2, 6, -1, and -4. My power x to the 2, 3, 4, 5. If I were to multiply this all out, the leading term would say x to the 5th, a bunch of extra junk on it. So I'm expecting this kind of a thing, expecting it to go up here and down here and do some kind of crazy junk in the middle. And now I'm just going to approach each 0. At x equals -4, I have x to the 1. This should look like a line. At x equals -1, that's to the 1, so it should look like a line. At x equals 2, this should look like a parabola, so I'm just going to bounce off. And then at x equals 6, should look like a line. There's my graph. I hope this has been a helpful and informative video for you. Be sure to tune in for the next one.